Hello friends, welcome back to STM tutorials. Myself Ajinkya and we are going to learn about STM controller. So in this video, we will be covering how to use the timer and how to generate the desired pulses. So first create new project using this file, new STM32 project. Give the project name. So it will initialize the target selector. In the MCU selector, select STM32 F103 C8. C8 and click on next. Give the project name, click on next and finish. As I have already created this project, now go into pin configuration, go into timers. So we are going to use timer 1 for the timer pulses generation. So here select the clock source as internal clock, then timer 1, PWM generation channel 1 and channel 2 as PWM generation CH2. Once you have selected this, you can see here these two pins will be selected as timer outputs. So on these two pins we will get our pulses. So if you go here, you can see that we can load our ARR count here, then repetition count, then we can select the desired pulses. Okay, so we can select this configuration, but we will be changing our configuration in the code itself, so we won't be messing with this configuration here. Once you have selected that, go into clock configuration. Now we have 8 MHz crystal oscillator on the blue pill board, so select that. So before that, go into system core, select RCC and select high speed HSC clock as crystal ceramic resonator. Then go into crystal configuration, select HSC as a PLL clock source multiplier, system clock source as PLL, select PLL as multiplied by 9, then our system clock will be generated as 72 MHz. Here you can see that the timer clocks are already set to 72 MHz. That means the maximum clock, system clock that our timer will get will be of 72 MHz. Now generate the code. It will generate the code. Then click on drivers, click on HAL driver, click on source, click on timer.c, HAL timer.c and click on open. So in this, you just go down, scroll down, then select HAL time PWM start, and you can find this function, copy this function and paste it here. Just the prototype declaration. Then write we are using timer 1, so HTM1, and we are generating pulses on channel 1 and channel 2. So we have to initialize both the channels. Once declared, then we will write our code here. Okay, so you can copy this code. Here I have stopped the timer, so timer won't be running and our channel 1 and channel 2 pulses won't be generating when this instruction is executed. So we are stopping the timer. Now we are generating the prescalar. We are setting the prescalar to 72. Now we want to generate the pulse of 62 milliseconds. So we are giving the prescalar as 72 megahertz. We are setting the timer as 62,000. Then we are setting the CCR value 1. So our timer will generate pulse of 62 milliseconds with on period equals to 11 microseconds on both the channels. So on period is set with the help of CCR1 registers. After that we are again initializing, or we are again turning on our timer. So at this point the timer pulses will generate. Now build the code. So here you can see that we have 0 errors, 0 warnings. Now as you can see, we have not written anything in our while one loop. So we are not processing anything in the main loop. We are just initializing our timer and we are just generating the pulses. Now we will dump the code into our controller. For this you use STM32 ST-Link utility. Press the reset button on your Bluetooth board. Connect to target. Release the reset button. Now it will connect to your STM board. Now press Ctrl P. Give the file location of your hex file and click on Start. Now it will dump your code into our STM controller. Now I have connected pin output to the logic analyzer. So we can see the pulses on the logic analyzer. Now the logic analyzer is capturing these pulses. We just want to check on period and total period of one pulse. So zooming in, here you can see that our total period is 62 milliseconds. Now we will check our on period. As you can see that on period of the 62 millisecond pulse is only 11 microsecond as we have said. Now here we will change it to 200 millisecond or 500 microsecond. We will change this to 500. Again build the code. Again dump the code into STM controller. Now we will check the pulses. Now here you can see that the total period of the pulse is 62 millisecond and on period is changed to 500 microsecond. Now the question arises that how we have calculated the total period and on period of each pulse. So the formula for calculating the total period T is ARR equals to clock frequency into T, that is desired time, minus 1. So we have to load this count into our ARR register. If I want to generate a pulse of 100 microsecond and when the clock frequency is set to 72 megahertz, then our ARR count will be 7200. Okay. Now, if I want to generate a pulse of 10 milliseconds, then the ARR count will be 7,20,000. But our ARR register is only 16-bit. The maximum value that we can load into our ARR register is 65535. Right? Now, for this, to generate this 10 millisecond pulse, we cannot load this ARR count. Now we have to make an arrangement. So there is one register called prescalar. So we can set this prescalar register. Then we can again calculate for our 10 millisecond pulse, the ARR count will be 1,80,000. Now it is obviously reduced, but it is still greater than 65535. Now then we again have to change the prescalar value to higher. Now it is set to 8. Again the ARR count comes as 90,000, which is again greater than 65535. Now we will set the prescalar value as 12. The ARR count comes as 60,000. Now we can load this value into our ARR register to generate the pulse of 10 millisecond. Now how to calculate the CCR, that is to generate the on time of the pulse, which is tau. Now if the prescalar is set to 0 and the ARR count is 7200 for 100 microsecond pulse, if you want tau as 10 microsecond, then we will be needing CCR value as 720 using this formula. So what the CCR formula is? It is duty cycle into ARR. So count to be loaded in ARR register into duty cycle. Now how we calculate duty cycle? It is simple as the on period divided by total period. It is duty cycle. Now for 10 millisecond pulse, we want tau as 100 microsecond. So the CCR value, the ARR value we calculated as 60,000. The CCR value will come as 600. Now if we want to change the tau as 300 microsecond for the same 10 millisecond pulse, then we will recalculate the CCR value and it will come as 1800. So CCR decides on time and ARR decides the frequency of the pulse. So here you can see this. The ARR decides the frequency and CCR decides the on period. So we have generated on period as same. If we change the on period, now we will change the on period. We will load the program into our STM controller. We will again check. Now here you can see this, the pulse 1, it is the on period is 500 microsecond and for pulse 2 it is 300 microsecond. So as per our code, it is 500 microsecond and for pulse 2 channel 2 it is 300 microsecond. So that's it for the video. Hope you enjoy the video. Hope you like the video. If you like and enjoy the video, click on like, share and subscribe. That's it for today. We will see you in the next video. Thank you.